In this video, we're going to explore reaction stoichiometry. This is a description of the quantitative relationships among substances as they participate in a chemical reaction, or more succinctly, the molar ratio between each of the substances involved in a reaction. In the last video, we learned how to balance chemical equations, and we ended with this chemical equation, which tells us that 2 moles of octane burned in the presence of 25 moles of O2 will give us 16 moles of CO2 and 18 moles of H2O. So if we start with 2 moles of octane, and we want to know how many grams of octane that is, well, we'll just calculate the molar mass of octane by saying 8 times 12.01 grams per mole. This is 8 moles. Oops, how about I rewrite that and use my units a little bit better? 8 moles times 12.01 grams per mole, and 18 moles of hydrogen at 1.01 grams per mole should end up with 96.08 grams of carbon per mole of octane and 18.18 grams of hydrogen per mole of octane. That gets us 114.26 grams of octane per mole of octane. So if we want to figure out how many grams of octane we're starting with, if we start with 2 moles, that's simply 2 moles of C8, 8H18 times 114.2 grams per mole. So we're looking at a mass of 228.52 grams of octane. This is what we started with. If we're interested in finding the mass of CO2 that we would make, well, we do the exact same thing. The molar mass of CO2, we'll calculate that by saying, well, there's 1 carbon times 12.01 grams per mole, and we have 2 moles of oxygen times 16 grams per mole. So we'll add together 12.01 and 32 grams, and we should end up with 44.01 grams per mole of CO2. And we know from the balanced chemical equation that our stoichiometric ratio between octane and CO2 is 2 to 16. So we know that we get 16 moles of CO2 out of this reaction. Multiply that by 44.01 grams per mole. We'll get a mass of 704.16 grams of CO2 if we burn 2 moles of C8H18 in 25 moles of O2. Okay, but what if I started with an amount of octane other than 228.52 grams? What if I started out with 200 grams or 500 grams or 20 grams? Could I use the same rationale to figure out how many grams of CO2 I would make? Absolutely, because the stoichiometric ratio is always the same. No matter the amount that I start out with, the ratio is always going to be the same, and the molar masses are always going to be the same. So now we'll end up with a dimensional analysis type of problem where we use the stoichiometric ratio and the molar masses as conversion factors. Let's get to it. I want you to look at this problem and plan it out. Please don't try to do the problem. There's some values I need to give you, but please pause the video, read the problem, come up with a given, find, and plan. Welcome back. Okay, this is quite the problem. So I live pretty far away from Oregon Tech, and this year we're doing distance learning with this class, so maybe I'm not having to drive every day or every week, but I have to drive normally to get into the office pretty far, and I burn about 7 gallons of octane doing that, assuming that all the fuel that I'm burning in my car is octane, which it isn't, but we're going to make some assumptions here. So if I burn 7 gallons of octane driving from my house to Oregon Tech, then the question is, how many pounds of CO2 do I put into the atmosphere during my commute? And what I wanted you to do was just come up with a plan. So let's go through that together. If I'm given gallons of octane, and I want to find, let's see, did I say pounds? So mass of CO2 in pounds. I'm going to have a lot of conversion factors. Let's make our list of conversion factors while we do our plan. So somehow, if we can get from gallons to moles, let's go ahead and give myself a little bit more space here. We can get from gallons to moles of octane. Well, for moles of octane, I can use that stoichiometric ratio to get to moles of CO2, like we did in the previous example. And for moles of CO2, I just use molar mass to go to grams of CO2. And then I could convert using some conversion factor between grams and pounds of CO2. So that's not too hard. Going from gallons to moles is a little bit more challenging, and let's talk about how we would do that step. Well, we know if we can get to grams of octane, we can get to moles using the molar mass. So if we got to grams of octane, we could use the molar, use a different color here for molar mass. What would we use to convert between gallons of octane and grams of octane? Well, gallons of octane, this is a volume, and grams of octane, this is a mass. And what conversion factor has units of volume and mass? Density. So, if we can look up the density of octane, we can get from gallons to grams. Then we already know the molar mass of octane. We just calculated it in the previous example. And then we get to moles of octane. And then we'd use our stoichiometric ratio from this 2 to 16 stoichiometric ratio. To get to moles of CO2, and then we'd use our molar mass of CO2 to get to grams of CO2, and then we need a conversion factor of grams to pounds, which we can look up. Fantastic. I think we're ready to do this problem. So I need to give you for this problem, or you need to look up conversion factors for grams to pounds and density. Everything else you already know. So here we go. I'm giving this to you here, the density of octane, and I'm even giving it to you in units that you can use right away. You don't have to convert. That's really nice. The molar mass of octane, we just calculated that in the last problem. That was 100, oops, get this pen working, there we go, 114 0.26 grams per mole. The mole ratio from octane to carbon dioxide, 2 to 16. Yeah. Molecular weight of CO2, we already calculated that at 44.01 grams per mole. I think we're ready. Let's do it. Let's get blue again. We're going to start with 7 gallons octane. I'm writing the octane below the gallons, but I'm not writing a line. So this is not gallons per octane. This is gallons of octane. I'm simply stacking them so that we have enough space. Our first conversion, we were using density, and we want to get rid of gallons of octane and get to grams of octane. That conversion factor was 2,620 grams per gallon. So the 2,620 goes on the top, gallons go on the bottom. Again, one of the most common errors that I see is those being swapped. The next step is using the molecular weight of octane to get to moles of octane. So we're going to put grams of octane on the bottom and moles of octane on the top, and we know that's 114.26 grams per mole. And the next step is going, oops, that's ugly, let's get rid of that. There we go. The next step is getting rid of moles of octane and going to moles of CO2. And that is 2 moles of octane to 16 moles of CO2. Where did we get that? We got it from the balanced chemical equation. Now we're going to go from moles of CO2 to mass of CO2. 1 mole of CO2 is 44.01 grams of CO2. Yep. And I am now in grams. My conversion factor is in kilograms. I could do this one of two ways. I can convert grams to kilograms here in my dimensional analysis, or I could do a second setup here where I convert pounds into grams. I'm just going to do the former, where I just add in one more step because I know that I have 1,000 grams in 1 kilogram. So we'll just toss that quick extra step in there because I'm already going to pick up my calculator for this. Okay, and then the last thing is knowing that 1 kilogram of CO2 is equal to 2.2046 pounds of CO2. Let's double check. Gallons of octane, gallons of octane. Get rid of those to grams of octane. Get rid of grams of octane to go to moles of octane. Get rid of moles of octane to go to moles of CO2. Get rid of moles of CO2 to go to grams of CO2. Get rid of grams of CO2 to go to kilograms of CO2. Then get rid of kilograms of CO2 to go to pounds of CO2. Now we just need to pick up our calculators once and plug this in. We should end up with 124 pounds of CO2. Wow, that's a lot of CO2 that I put into the atmosphere. Now, let's complicate matters. We live in a bit of an imperfect world, as I think we all know. What if my car is running really rich? So that could happen if, say, my O2 sensor was broken and not enough oxygen was let into the reaction chamber. Okay? So if we don't have enough oxygen getting let into the reaction chamber, Are we going to completely consume the octane that we've injected into my engine? No. Would we end up with the max amount of CO2 that we just calculated? No, we wouldn't. So let's explore this, and then we're going to start by just writing out this equation once again. So we have 2 moles of octane that reacts with 25 moles of O2 to make 16 moles of CO2 and 18 moles of water. So what's happening when my car is running really rich is the car computer is not doing the correct math. So it's putting in 2 moles of octane, but it's not putting in 25 moles of O2 for each amount of 2 moles of octane. Okay, so the ratio is no longer 2 to 25, which means that I can't get out my max amount of CO2 because I'm not going to have enough oxygen to make that 16 moles of CO2. Yikes. So how are we going to do that math? How can we figure out how many moles of CO2 I'm making? We can use dimensional analysis to calculate how many grams of O2 we need in order to have that 2 to 25 stoichiometric ratio. So we do that by saying we'll start with 7 gallons of octane, and we can convert that to moles of octane, then use our 2 to 25 stoichiometric ratio to convert that to moles of O2 needed to complete that reaction, and then to convert it to grams of O2, we simply need our molar mass. Okay. So let's set up this dimensional analysis. 7 gallons, C8H18, get to moles. We want to go 1 gallon is 2620 grams. Going from grams to moles, we know that 1 mole is 114.26 grams. And then we want our molar ratio here. We know that 2 moles of octane, we need 25 moles of O2. And then to convert that to grams, 1 mole of O2 is 32 grams of O2. Double check. Gallons, gallons, grams, grams, moles, 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 moles to grams. Plug that in, we should get 64,204 grams of O2. This is how much O2 we need to completely use up that 7 gallons of octane that we put into our fuel injectors, through our fuel injectors. So what if my engine only let in 25,600 grams of O2 in? if we were able to measure how much O2 goes into the reaction cylinder, and that value was 25,600 grams of O2, then we could go ahead and calculate how much CO2 we would expect to make. So we'll call this A, part A of the question. And then we would be able to figure out how much octane is being wasted in this reaction. And we're going to do this again using dimensional analysis. So for part A, we'll start with what we're given, the 25,600 grams of O2. And we want to go to CO2. So it's going to be very similar to the dimensional analysis that we've done before. I'm not going to go through the whole plan. I suggest as you're learning how to do dimensional analysis, you do the plan and then you do the setup. But I'm going to go straight through because this is just another example that is very similar to the examples we've been doing. So for O2, we want to convert from grams to moles before we can then convert to moles of CO2. And we know that O2 is 32 grams per 1 mole. And if we go back to our balanced chemical equation, we know that we get 25, or we use 25 moles of O2 for the 16 moles of CO2 that we get out. So now we've converted to moles of CO2 and we want to go to grams of CO2 before we can convert to pounds. We know that 1 mole of CO2 is 44.01 grams. Then we're going to convert to kilograms, 1,000 grams in 1 kilogram of CO2. And now lastly, we'll convert 1 kilogram to pounds. And we can plug this into our calculators and we should get out 49.7 pounds of CO2. So this is what we would expect to make given that we have a certain amount of oxygen. Next up, the question is, how much octane am I wasting? In order to do this problem, we first need to calculate how much octane we need to use if given this amount of O2. So we know that we have an excess of octane, and we know that because we know we would need 64,000 grams of O2 and we only have 25,000 grams of O2. So we're limited, our reaction is limited by the amount of O2. So we're going to start with O2 and calculate how much octane we would need based upon that amount of O2, and then we'll subtract. So we're going to do this in two parts. One, dimensional analysis, where we're given 25,600 grams of O2, and we're going to find gallons, that's right, gallons of octane. And then the second part, we're going to subtract gallons of octane that we burn, that's 7, minus gallons of octane needed. So there's our plan for B. Yeah? And we have a second slide for doing that math. Again, we're going to start with 25,600 grams of O2, and we're going to convert to moles of O2, then moles of octane, then to gallons of octane. So this starts out the exact same way that we did earlier, 32 grams of O2 per 1 mole of O2. We know that we burn 25 moles of O2 for every 2 moles of octane that we burn. And we have a molar mass of 114.26 grams per 1 mole of octane. And then we convert grams to gallons using density. 2,620 grams per 1 gallon. And now we plug and chug. We should get 2.79 gallons. So that was part 1, and this is part 2. We want to figure out how much octane we're wasting. Well, we said we're burning 7 gallons, and we actually only need 2.79 gallons based upon how much O2 is being used. That's a huge waste. We're wasting 4.21 gallons of octane during my commute. Now, besides the fact that this is a lot of dollars, it also would gum up my engine and be overall pretty bad news. Thankfully, my car is not that inefficient. So in this problem that we just did, we introduced some terms, and I want to go over these terms again. So we were limited in our reaction by the amount of O2. We had an excess of octane, so that's our reactant in excess, and our limiting reactant was O2. And we calculated a theoretical yield of CO2. So again, I'm going to just fill this out. Limiting reactant was O2, reactant in excess was octanol. And you may see me write excess, because if you say that, it says excess, okay? And our limiting reactant was O2, and then our theoretical yield was CO2, and that was 49.7 pounds. Not the 140 or 25 pounds or 24 pounds that we calculated earlier based upon the octanol, because we were limited in the reaction by O2. So when we calculate our theoretical yield from two different reactants, our theoretical yield is actually the smaller of those two answers. In general, the theoretical yield isn't the actual yield that we get out of reactions, because usually there are things called side reactions and incomplete reactions that make our theoretical yield not the same as our actual. So in order to figure out the efficiency of a reaction, in chemistry we calculate the percent yield. So this is telling us how efficient a reaction is. And in order to do that for this particular example that we're working, we would need to determine how much CO2 we're actually making. So if I put a CO2 detector on the tailpipe of my car and I found that my actual production is 15 kilograms, then I can compare 15 kilograms, that's my actual, to my theoretical, which is 49.7 pounds. But before I can do this percent yield calculation, I need to make sure these are in the same units. So I either need to convert my 15 kilograms to pounds, or I need to convert my pounds to kilograms. We'll go ahead and do the latter. So our first step is going to be converting 49.7 pounds to kilograms. Know that 1 kilogram is 2.2046 pounds. So this should then be 22.5 kilograms. So our second step is calculating our percent yield. And this is pretty simple. We're going to take what we actually got, that's 15 kilograms. We're going to divide that by 22.5 kilograms. And we'll multiply that whole thing by 100, and we should end up with a 66% yield. So we've done a lot of different conversions in this class already, and this figure simply shows you all the different conversions you can do and all of the conversion factors, that's these here, conversion factors, that you need to use to do these conversions. I highly recommend that you spend some time with this and make sure you know how to do each of these conversions, and if you don't, please come to my office hours. One last thing before I set you out on practice problems, I want to start one problem from the ground up. So we've been following one example and learning about it, and now this is kind of the type of problem that you would see. So if I gave you a reaction, I could tell you how much of the reactants I've started with, and then I'm asking you, what was the percent yield if this is what I obtained coming out of it? So there's a number of steps that we need to do to tackle one of these problems. The first one is check to see if the equation is balanced. Then we need to figure out what is our limiting reactant. Because I've told you that I've given you some sodium chloride and some water. I don't know which one is my limiting reactant, so we have to figure that out. Then we're going to have our theoretical yield from our limiting reactant, based upon how much we have of our limiting reactant, and then we can calculate our percent yield. So this is a 4-step type of problem. Step 1, we're going to rewrite the reaction. And this should have been liquid. I'm sorry, I forgot to put that on there. We'll build our table. Reactants, products. We have sodium, chlorine, hydrogen, oxygen. Sodium, chlorine, hydrogen, oxygen. We're going to start with 1 sodium, 1 chlorine, 2 hydrogen, 1 oxygen. We'll start with 2 chlorine, 3 hydrogen, 1 oxygen, and 1 sodium. So the first thing that stands out to me is that the things that are different are hydrogens and chlorines. I'm going to go ahead and just put a 2 in front of our NaCl. Let's see what that does. Now we're going to have 2 sodium, 2 chlorine. So now what's off are our sodium and our chlorine and our hydrogen. So let's go ahead and put a 2 here in front of our NaOH. We'll get back with our sodium, and now our chlorine's on. Our hydrogen, we have an 2 here, and then 2 here, so now we have 4 hydrogen here. And so we also have changed our oxygens. We should have 2 oxygens. So now we can go back and put a 2 in front of our H2O, and we're only changing hydrogens and oxygens, and we're doubling it, so we should have 4, and we should have 2. Oh hey, look, there we are. We'll double check. We have 2 sodium, 2 chlorine, 4 hydrogen, 2 oxygen. We have 2 sodium, 2 chlorine, 4 hydrogen, and 2 oxygen. Well, we're done balancing that equation. I'm going to go ahead and make this small, move it up here. Okay. And just to highlight, putting a 2 there, a 2 there, and a 2 there. So now we have our balanced chemical equation. This is really important because we get our stoichiometry from the balanced chemical equation. If our equation isn't balanced, our answers will likely be incorrect. So then that was step 1. Step 2, we want to figure out what our limiting reactant is. Now, we could do this a variety of ways. We can convert and see how many moles of each, because this is a 1-to-1 molar ratio, we can just see how many moles we have and compare those two. And for a quiz, that would be a completely acceptable type of answer. However, I'm going to look forward and say, well, the whole idea is to figure out the percent yield. And so if I just take this dimensional analysis one more step, I can convert to how much Cl2 I'm going to get, and I might as well take it a second step further and just get grams of Cl2 for my theoretical yield for both my sodium chloride and my water, and then I can figure out which one's my limiting reactant, and I can get my theoretical yield all at the same time. So steps 2 and 3 I'm going to do simultaneously. So we'll do it first for NaCl. We start with 10 grams of NaCl. The molecular weight, sodium chloride, should be 58.44 grams. Get 1 mole. Now we're going to convert that to moles of Cl2. We have 2 moles of NaCl per 1 mole of Cl2. And then we'll turn that to grams. 1 mole of Cl2 is 70.91 grams of Cl2. We plug and chug this, we should get 6.066906 grams. Notice that even though I only have 3 sig figs that I'm starting out with, I'm going out to all my decimal points because I want to make sure that I don't have a rounding error. We'll round at the very end. So now we do the exact same thing with water. I have 10.0 grams of water. So we'll convert grams to moles. That's 18.01 grams per 1 mole. And again, 2 moles of water, 1 mole of Cl2, 1 mole of Cl2 is 70.91 grams of Cl2. Plug and chug this, and we get out 19.686285 grams. So which one is our limiting reactant? We choose the smaller of the 2 answers because we can only make as much as our smallest amount dictates. So NaCl is our limiting reactant. H2O is our reactant in excess. And now we can do step 4 and calculate our percent yield. So this is in grams, this is our theoretical yield. And this is our actual yield, 3.58. So we will take our actual over our theoretical, 3.85 grams over 6.066906 grams times 100. We get 63.95%. We can only do 3 sig figs, so we have to round to 64% yield.